In the previous videos, we defined cointegration and we looked at various cointegration representations. In this video, we will learn how to set up a cointegration test in the single equations framework. Remember, I started this lecture with these two pictures. All non-stationary time series, but on the right, they were cointegrated and moving together in the long run, whereas they aren't on the left. And a crucial difference was the unit root behavior of this linear combination in this case. The picture on the left still had a unit root, whereas the picture on the right didn't. So intuitively, we feel that if y1 and y2 are cointegrated, then the trends in the individual series will not cancel out. So in other words, if y1 and y2 are not cointegrated, then any linear combination of these series still has a unit root. So if we are able to perform a unit root test on a linear combination of x and y, and this test would indicate that it is stationary, then we would find evidence of cointegration. So this is also our test for the null of no cointegration. So this is also how our test will work. We estimate here this regression for the series in levels, and we obtain our estimator beta hat just with least squares. Now, the residuals of this regression are nothing more than a linear combination of our two original series. So if the residuals would be integrated of order 1, then we would not have cointegration and we would be in the spurious regression framework. If, on the other hand, the residuals would be stationary, then we would have cointegration. So we would like to apply our unit root test on the residuals in order to determine whether we have cointegration or not. And that is also what we will do. Now, some remaining remarks before we set up this test. Well, in the previous weeks, we looked at this model and tested the null hypothesis of a unit root, so rho equal to 1 in this model. But this is actually equivalent to testing the nullity of the parameter phi in this equation over here. Why? Well, simply start from the top equation and subtract yt minus 1 from both sides. So yt minus 1 is subtracted here and there. On the left-hand side, you immediately recognize then the series indifferences. And on the right-hand side, we have rho minus 1 that pops up as the new parameter in front of this lagged value of y. And so I call this new parameter phi. And then testing the unit root null of rho equal to 1 is indeed equivalent or boils down to testing the nullity of this new parameter phi, because phi is nothing more than rho minus 1. Now, to set up our test for the absence of cointegration, we will only look at the IID case for the error terms. You can, of course, again, relax that to allow for serial correlation, but the mathematics become immediately much more involved without actually giving you more intuition beyond this basic case. So that is why I prefer to go through the roadmap of the basic case for IID errors and bring intuition across in that setting. So in order to set up our cointegration test, it is crucial to remember that under the null, we do not have cointegration. So in other words, we start from the spurious regression framework from last week. Define also this new vector zt that collects yt and xt and is then of dimension k. So we have in total k plus 1 series among which we would like to test for cointegration. Now, since all series are non-stationary, we have a random walk model for ZT as denoted here on the slide, and we work with this initial condition. Now, in the most simple case, we also say that the error terms are IID normal with no contemporaneous correlation. So we have an identity matrix of dimension k+1. No surprise that we will again have to rely on the functional central limit theorem, this time for our vector process epsilon t, where this guy converges in distribution to a k+1 vector of independent Brownian motions. Now, how does our roadmap for setting up a co-integration test look like? Well, remember, we want to test the nullity of the parameter phi in this test equation, where the eta hat t's are the residuals from the regression of yt on xt. So we investigate the unit root behavior of these residuals, the eta hats. Now, in order to arrive at the limiting distribution, we need to go through a couple of steps, since this time we are actually performing a unit root test on an estimated series, the residuals, in which the estimator beta hat appears. So first, we need to derive the limiting distribution of beta hat. And so once we have this limiting distribution, well, then we can retrieve the limiting distribution of phi hat here in our test equation. And there we just start from the least squares estimator, the definition of the least squares as usual. In a final step, we then need to take care of all the quantities that pop up in our test statistic for testing the null hypothesis that phi is equal to 0. So let's now go through all of these steps one by one, starting with step 1, the derivation of the limiting distribution of beta hat. So step 1 over here on this slide. As always, we start from the definition of the least squares estimator, and then we introduce the appropriate scaling for the two terms that are involved. Since they follow a random walk model, you can plug in the respective partial sums of the error terms to arrive at this limiting distribution over here. Both terms need indeed scaling by 1 over t squared. You need 1 over root t on this guy to recognize a partial sum process. Similarly, you need 1 over root t to rewrite this guy as a partial sum process. And then you need an additional 1 over t for the width of the interval to recognize a Riemann sum. Note that I don't write out the details here anymore, since this is very similar to what we did the last week for the spurious regression framework. Have a look at those slides again to verify these limiting distributions. Okay, so since we need this limiting distribution in our following steps, I will compactly write this distribution down with this new notation zeta w. Step 1 is done. What is step 2? Well, in our second step, we care about the limiting distribution of the estimator for phi in our unit root test equation. So let us introduce here some new notation to be able to write everything down compactly. The residuals are a function of my estimator beta hat. So it's only natural that that guy's limiting distribution will pop up. So let's introduce here this new vector psi w, whose limiting distribution has then, of course, the limiting distribution of beta hat that we derived on the previous slides. Now, why is this notation convenient? Well, remember that our eta hats that are popping up in the expression of our estimator, well, the eta hats are nothing more than the residuals of the regression of the series in levels on each other. And I can compactly express these residuals, the eta hats, as the product of zt, the vector that collects yt and xt, so the product of zt with this new vector psi hat w. All right, so with this new notation, I have everything in place to introduce the appropriate scalings in numerator and denominator of the least squares expression for phi hat. In the numerator, after plugging in this expression for eta hat, which I summarize here below, I've managed to rewrite it in a form where psi hat appears. Remember psi hat that contains beta hat, and this cross product term. Remember, zt collects all series that have a unit root. And in the previous tutorials, we've seen that this guy needs scaling by 1 over t to converge in distribution to this integral of our Brownian motions. And then we just need to plug in the limiting distributions for the psi hats, which contain the limiting distribution of beta hats. So now we're done for the numerator. What about the denominator? Also for the denominator, I rewrite my eta hat, the residuals, in terms of the zeta vector times the psi hat w. And now I have a cross product of zt's, which again have unit root behavior. And in the previous tutorials, you've seen that this guy requires scaling by 1 over t squared. In order for, let's say, okay, each guy over here needs 1 over root t to recognize a partial sum, a scaled partial sum, and you need an additional 1 over t for the width of the interval. So in total, you need 1 over t squared to arrive you at the limiting distribution as displayed on the slide. On the next slide, I then combine all of the results that we derived from the previous slide to see that the asymptotic rate of convergence, or the factor by which we need to blow up this guy, is t. Now we're almost there. Step 2 is done. In the third and the final step, we need to find the limiting distribution of the test statistic, testing the nullity of phi. We start from its definition, estimator minus quantity under the null, which is phi equal to 0, divided by its standard error. And the only new ingredient is the variance estimator of the residuals, which is defined over here. After again plugging in the definition of the residuals and rewriting our eta hat like we did before, we can expand this product in this way, where all of the terms appear. Just like in the previous cases, the stochastic orders tell us then that there is only one dominant term, the first one over here, which converges in distribution to the cross product of the psi's, since the variance-covariance matrix of the error terms was equal to the identity. Now, if we turn back to our test statistic, after some rewriting and introducing the appropriate scalings, we actually know the asymptotic behavior of each entry that is involved. You can check that, that I've just combined all of the pieces from the previous slide together into this limiting distribution. So let's take a pause and look at this limiting distribution. Note that only standard Brownian motions pop up. So no nuisance parameters, since we actually assume that our error terms are IID normal with variance covariance matrix equal to the identity. We can again obtain the critical values from simulation, where this time, of course, our limiting distributions depend on a k+1 dimensional Brownian motion. So the limiting distribution will depend on what k is, the number of predictors we include in our original regression. These critical values are also tabulated in Hamilton. And we have a unit root test over here, but it is not the classical Dickey-Fuller distribution that we get as a limiting distribution. Why? Well, we do not perform a unit root test on an observed series, but on an estimated series, on the residuals of this initial regression of the series in levels on each other. And the limiting distribution of our estimator in the initial stage, namely the beta hat, is popping up through the psi vector. If we would, however, not have this initial regression, so when the second component would be 0, then we would retrieve the Dickey-Fuller distribution again. So the extra terms are just due to the initial regression in levels that we perform to obtain the residuals on which we need to perform our unit root test. All right, so now one question that remains is what happens to our test under the alternatively, namely when we do have co-integration, and that we will verify in the tutorial.